Okay, this was the general expression which we had discussed in the last class. The change in entropy is always taken in place in respect to the initial entropy, and the final entropy is actually what you are calculating. But since we are always calculating with only the entropy change, we are actually not going to write, but we can write in terms of the initial entropy and the final entropy. And if we do that, we had taken this as the general expression for adiabatic process. What should be the entropy change? We had said that the dq reversible is going to be 0 because it's an adiabatic process. So the initial and the final entropy will remain the same. So the entropy change for that particular process is going to be 0. If I have an isothermal process, I had replaced the dq reversible integrated over from state 1 to state 2, and dq, if it is isothermal process, we had taken delta u to be 0. Isothermal process means the temperature is not changing, so delta u is equal to 0. And if delta u is equal to 0, then delta q is going to be equal to the w minus w. So if it is a reversible process, so if it is a reversible process, only then we can substitute the dq reversible. So all the processes which we are talking about is derived based on reversible conditions. And this reversible conditions, if you remember what was the work done for a reversible isothermal process, was nRT ln V2 by V1. So if you substitute that, you can the T denominator is going to be cancelling off with this T, and so you get a expression of delta S for an isothermal expansion for an ideal gas. When we had an isochoric process means the W is equal to 0. You have no volume change. Isochoric means volume is constant. So the isochoric process, the work in the process is going to be 0. So the internal energy change will be equal to the heat transferred at constant volume, and that is nothing but CVDT. So if you have CVDT, you can plug in the equation of the entropy change for dq reversible by T, and this is obviously going to be a reversible process which we are taking into account. So this will be the heat transferred at constant volume under reversible condition. So if you substitute that, you get the expression delta S at constant volume process for the constant volume process is going to be CV ln T2 by T1. I hope you have remember these. We are going to talk about a few more things today, and I'm going to do a small numerical in the class. Let us see how much time permits. So if I have a heating at a constant volume, so we know that if it is a heating at constant volume, what will be happening? We have said that the same thing as isochoric process. This is what we are talking. We are talking about a heating at a constant volume. So heating at constant volume, the V becomes equal to 0. So the delta U change will be equal to the CVDT. So we can write down this expression. What happens when you have reversible expansion at constant temperature? I have not put any condition here, so the general expression will remain in terms of the temperature and volume, and from there you can take the temperature off because temperature is constant. Depending on what the parameters are given, you can take in terms of P or you can take it in terms of V. So we are going to take one example of this today. And what we had just mentioned but not taken up, and I had said I'm going to take up today, is the reversible heating for a substance or cooling, whatever it is, when there is a phase change associated. When there's a phase change associated, then the dq reversible at constant temperature and pressure becomes equal to the enthalpy change for the process. So the enthalpy change is replaced instead of the dq reversible, and you get a delta S equal to enthalpy change of that process, whatever phase change we are talking about, divided by the temperature of transition of that temperature, whatever temperature transition you are associating. Now, if I have to write a general expression, if I want to write a general expression of entropy change, it is better to remember this way. If it is also having a phase change, if it is also having a heating process, then the entropy change, we usually say that entropy change is measured with respect to T equal to 0. So the entropy change is going to be entropy at the given temperature into the temperature entropy at the temperature 0. This I'm going to mention why I'm taking this now. Then we have, if it is a solid to a gas conversion, then I have the CPdT. Then I have the corresponding fusion enthalpy change. Then I have the liquid state. That means solid is converting to liquid, and then liquid is converted to gas. So you have the two enthalpy changes, phase changes taken into account. Until you do an example of this, it becomes very bookish, and I hope you are writing down what we are talking, because if I'm going to ask you to do the problem right now, you should know the expression. So what if I have a continuous process of a solid being heated from a low temperature to a gas phase, then I not only make them into small say phases in which I do the calculation. First, I do the calculation at if the Cp of the solid is given, then I say take CpdT and find out what is the entropy change. And then I go to the fusion process where I have the fusion delta H fusion divided by the transition temperature of the fusion transition temperature. Then I have the liquid state. Liquid state, I have to find out what is, if I have go to the temperature, what will be the entropy change. That will be again Cp of the liquid dt divided by T. You can find out what the change of entropy is. Then finally you have the evaporation. So vaporization, enthalpy of vaporization divided by the temperature of transition. Then finally the at temperature at which you are calculating the delta S, or the S for that particular temperature, will be the Cp of that gas divided by T into dt. So that will be depending on which temperatures you are taking, and these temperatures are going to be the final temperature you are supposed to compute the entropy change. So this being the background, this is a general expression which you should know for any a substance being heated from say low temperature to a gas phase. You have to break them in steps and calculate the entropy of each of this and add them up to find out the total change. Now, what about this entropy change at constant temperature and pressure? That's associated with the phase change. And in phase change is a reversible process or irreversible process? Phase change is a reversible process or irreversible process? Yes. Finally, what do you get? The two phases will be in equilibrium, right? If I have a if I have a transition from liquid to vapor state, suppose I'm a boiling water, then the boiling water will have a condition at equilibrium. The condition is at equilibrium. The equilibrium is reached when we have a phase transition. Okay. At phase transition, we have a temperature constant process where obviously we are doing under atmospheric pressure. The pressure is also constant. The temperature pressure being constant, what you are talking about is a phase equilibrium. Okay. Phase equilibrium means what? It is a reversible thing. At that condition, you some amount is getting vaporized and some amount is still in getting condensed. So these processes, all phase change processes, are reversible processes. If it's a reversible process, then the entropy change of the system will be equal to the entropy change of the surrounding with a negative sign, right? So if you are asked to calculate for an entropy change for the surrounding, you are asked to compute the entropy change for a surrounding for a phase transition process, a process where you are having a change in state. That time, you remember whatever system entropy you have calculated, that same value with a negative sign will represent the entropy change of the universe as surrounding. And what will be the entropy change of the universe? What will be the entropy change of the universe? What is entropy change of the universe? It is system plus the surrounding. So what will the entropy change be? Whatever you are getting for the system. Yes, so come up and say that. Yes, it is 0. So the entropy change of the universe becomes equal to 0 when you are having a equilibrium reached. So how long can it be carried out, or how long the process is going to happen, is going to be happening till the equilibrium is reached. That means no further changes occurring at that particular temperature. Okay, temperature is a constant at the phase change temperature. That temperature is held constant. So if I have an example of, say, liquid water at 0 degree at 1 atmosphere, and equilibrium with where you are having a solid, that means you have the fusion process. Solid and liquid are in equilibrium at 0 degree at on 1 atmosphere. So this is the equilibrium we are talking about. So if I have the delta S calculated for the system, I can write down what will be the entropy change for the surrounding, because it's going to be just equal and opposite. Now, what will be happening? Let us take a look. Entropy change will be always positive. Entropy should be always increasing. We do not get anything which is having negative entropy. So for a system where I'm computing the phase change, can I get an entropy of a system negative? See, it is going to depend on whether the delta H is negative or not, right? So if I have a process of vaporization, what is happening? Vaporization means what happens? Delta H will be negative or positive?
Positive.
Delta H will be positive. If I have a melting, delta H will be positive.
Negative.
Negative.
Melting
If we,
releases the heat, right? Oh, melting. Sorry, ma'am.
you are confusing with freezing and melting,
Yes,
right?
ma'am. So,
Okay, so freezing is negative, right?
yes, freezing will be negative.
Freezing is negative. So if you see this table, I've written down vaporization will be having an enthalpy which is positive. Melting will have a enthalpy which is positive. Freezing will have a negative enthalpy. So what will happen to the corresponding delta S of the system? The delta S of vaporization will be positive, and that is justifying your observation that whenever you are making a liquid change to a vapor phase, the entropy should always increase because you are going to a more disordered condition. Okay, and then you have melting, again solid being converted into liquid. The entropy this disorder is increasing, so entropy should increase. Now, what about the freezing? Freezing is actually from solid to liquid to solid. So you have a decrease in disorder. So you have a negative entropy. So negative entropy change is associated with the freezing process. But what will happen to the delta S universe? What will happen to the delta S universe for the freezing process? This will be opposite. If delta S system becomes a negative quantity, then this will become, the surrounding will become positive because it should be equal and opposite because they are in equilibrium, right? So the entropy change of the universe will be 0. So when you are asked to compute an entropy change and you get a negative value, you start questioning why are you getting a negative, because entropy negative you cannot report. But then you have to go back and see what are you computing? Are you computing the entropy of the system or the surrounding or the universe? The universe will always have a increasing entropy. Total entropy should be 0 if it is at equilibrium, or greater than 0. It should be always increasing. So you have to compute and see whether the universe entropy is positive or not. Okay?
Ma'am, ma'am,
Yes.
when we say that when phase transition occurs, the delta S universe will be zero. So
Yes.
what does it? What is the physical meaning? I mean, there is some disorderliness, right? While vaporization or melting, they
No,
are
see, entropy gives you two information of about how long the change will take place. Okay? And whether the change will take place or not. These two information is given from entropy, second law. Okay?
yes,
And how long is the answer to what you just the question you asked. How long the change process is going to continue. Process is going to continue until they reach their value which at equilibrium. Okay? And usually when you are having any process taking place, the entropy is changing. And it keeps on changing until you reach the equilibrium where you have the maximum entropy. Right?
okay.
So the
So
change will
it is
continue.
so at equilibrium the liquid state, for example, for the melting, the liquid state and
For
the
any
solid state, they
this is specifically we are talking about a phase transition.
yeah. So at
Okay?
phase transition they are coexisting together. That is why we say that the entropy is zero.
They are reversible and at equilibrium. Two things have to be remembered. They are reversible conditions and at equilibrium.
Okay.
You see, you put this sign, arrows in both the side.
Yes.
Okay? They are coexisting. The arrow means they are coexisting and they are existing in at equilibrium. Okay? So
Yes.
entropy change of the universe should be either 0 or greater than 0. For a system which is at equilibria, the value becomes equal to 0. Reversible process at equilibria is that where is the delta S universe becomes equal to 0. So all of these systems which you have taken, whether it is melting or evaporation or freezing, you can compute the entropy change of the system and then eventually calculate the entropy change of the surrounding, and then sorry, yes, and then you can compute the entropy change of the universe by adding the two. Okay. Now there's a rule here. There's a rule here which you must understand. It's the Trotton's rule. Trotton's rule states that for a wide variety of liquid, the standard entropy of vaporization of that liquid is given to be 85 kilojoules per Kelvin per mole. Okay. That means if I have to find out the boiling point of a liquid and I've given to use the Trotton's rule, then I know if I'm given the enthalpy of vaporization, then I should be able to calculate the boiling point, right?
Yes, ma'am.
Yes, delta H by T equal to the entropy change. Okay, at the particular temperature which we are talking about. The transition being the boiling point when we are talking about evaporation. So when I'm talking about a liquid, and I'm calculating the standard entropy of vaporization, that means what is given to me is the standard vaporization delta S for the system, right? So the standard entropy of vaporization is a fixed value for most of the liquids, approximately equal to 85 joules per Kelvin per mole. Now, if I am given the value of enthalpy, standard enthalpy change of vaporization, then I should be able to get the value of boiling point, right? Because delta S will be nothing but delta S into the transition temperature, right?
Yes, ma'am.
So for you can for if it is the question is given that the apply Trotton's rule to calculate the boiling point of some benzene for which the enthalpy change of vaporization is given to be so and so. Then you may not be given the value of entropy change, standard entropy change of the liquid at the vaporization stage. But you have to apply it using, if it is given using Trotton's rule, then you will take it as 85 joules per Kelvin, plug it in this, and whatever is given delta H value, and then find out the value of the temperature of boiling.
Ma'am, why does this rule work?
Why does the rule work? I'm going to say why it doesn't. Most of the liquids have, if they do not have any other associated properties, if there is some liquid which is having a lot of association, hydrogen bonding, then the rule is violated. If there is more interaction, if you just find out, if you say water molecules has hydrogen bonding. Please mute your microphone. So if you have water, then you have hydrogen bonding in the liquid, and that time the Trotton's rule is going to be violated. You will not get 85. It is around 109 for water. The interaction is increasing. Why is it so? Why is it so? The enthalpy change is associated with the intermolecular forces which is existing, type of bonds there, because we are talking about bond breaking here. Understood? That is directly, the entropy change is directly related to delta H, and delta H is related to the bonds which is associated in the molecules, right? If you have some sort of association or hydrogen bonding in the liquid, then that time the values which you are supposed to get is going to be slightly higher than what is standard, if you are taking a standard, if you are not computing what is the exact value. So if you have a liquid, then you will have more or less around 85 until the liquid has some extra qualities associated or extra type of interactions associated with it. So if you are asked to compute using Trotton's rule, you have to understand the liquid is following the standard, any liquid which is having no association or no extra strong intermolecular interactions in addition to being a liquid, whatever you are supposed to have. Okay? This is the Trotton's rule. Now, I'm going to look at this. It is a general expression. The whole thing I'm doing, I'm carrying out the computation part, but I have not actually discussed the main entropy thing of Clausius inequality. We'll come to that. So the entropy change of a system at a temperature T from the entropy value at temperature T1, which is the initial, and the heat supplied to the change can be given as a general expression, which I have just now written in the previous slide. This is a rewriting of that. On heating an ideal gas at a constant pressure, if you can see, how can you write? You can write down this initial, I have always said the initial temperature and the final temperature difference you are taking. If the initial value is given, then it is okay. Otherwise, you just say delta S for that particular system. If you have to see, if you are measuring Cp under constant pressure, this Cp should be constant at the given range of temperature you are doing the measurements. And you see the substance is going to, the entropy is going to change exponentially as you are carrying out the heating. Similarly, when you are having an ideal gas at constant volume, the expression is going to be replaced by Cp. Instead of Cp, you have now Cv. Here also, we have to ensure that Cv is independent of temperature in the range in which you are performing the computation or you are doing the experiment. And it's again also going to increase with increase in the heating. Okay. So when it is again logarithmically increasing, entropy of a substance is going to logarithmically increase, and it is going to, as it is heated at a constant volume. And each of these curves you see are representing various values corresponding to various Cp by R values for this. Okay, for a given temperature, you can find out one and then you can compute it. So we can understand that for an entropy change of a system at a given temperature is related to the entropy change of the temperature at 0 if I have to compute from 0. Okay, you see this in this expression. I am using the general expression here. Again, I have used the general expression. This is the general expression when you are starting from a temperature initial at 0. So I'm applying that equation here. So the entropy change of a system at temperature T is related to its entropy at T equal to 0. Okay, to determine, we need to know the heat capacity at each of the temperatures, and that is what we are going to discuss and give you the condition for that, and that is the third law. We are not going to discuss any further about the third law. We are just going to see how to compute the Cp from the T equal to 0, because usually you should be, until it is mentioned what is the initial temperature, you can calculate the entropy change from T equal to 0. So T equal to 0, if I can represent that, this will be a graph which is going to be looking like this. What I have a, first I have one entropy which is to begin with at temperature equal to 0. Then at from 0 degree to a final temperature for which the Cp is supposed to be known, Cp of that solid into dt by T. Okay, so this will be the curve, and all the area under the curve will give you the entropy change associated. So next what you have? Next you have the transition. Okay, these lines are going to mean the transition, and at transition what you have? You have the delta H fusion divided by the temperature of fusion. Then once you have already got the liquid, then you have to do a Cp dt by T for the fusion temperature to the boiling temperature. So from fusion temperature to boiling temperature, you are going to have this zone as the liquid. Okay, so that means the Cp should be constant around here in this region. Then comes another phase change. So phase change is delta vaporization at in the boiling point. So we are getting the boiling point enthalpy change, and you can compute the delta S. And finally, this zone will be from the temperature of boiling to any temperature which is supposed to be the final temperature at which you are trying to compute. So starting from 0 to the fusion temperature to the boiling, and boiling to the final temperature, you have two distinct phase change which is occurring, and you have to account for that. Now, using the Cp at different temperatures, the area under the curve of Cp by T or Cp Cp and ln T, if you plot either of the graph, Cp by T, the area under that curve gives you the entropy change, or you can take it Cp ln T, as the x-axis, and also that will also give you the entropy change. Okay, and the entropy change of each of the transition. If you can calculate this and the entropy change at the each of the transition, you can get the total entropy change associated. Now the problem is to measure the Cp at 0 degree, because we are saying that Cp of the value has to be computed. So when we are talking about very low temperatures, what will be the value of Cp? It is difficult to measure Cp at very low temperatures, which is approaching 0. At this temperature, what we apply is the Dubai's extrapolation to find out the value of Cp. This condition at where the temperature is very low, nearing to T equal to 0, that time the Cp value in computation is very difficult. What you take to calculate the Cp value is the Dubai extrapolation. The Dubai extrapolation says that Cp equal to a to the power T to the power 3 down to T equal to 0. So Dubai law, whatever you have for the Cp, is valid at very low temperature for a solid, and that is given by Cp equal to A into 10 to the power 3. Okay, The temperature, if you are having too low temperatures, then this approximation is valid. So entropy at very low temperatures, that is, this is known as the Nernst heat theorem, and that's the part of the third law, which states the entropy change accompanying any physical or chemical transformation approaches zero at the temperature approaching zero. That means as the temperature is approaching zero, the entropy of the solid is going to approach zero, provided all substance involved are perfectly crystalline. So what we have taken to compute the entire entropy change from zero to a temperature which of interest, we have seen that if I have to look into it, I have to find out the area under the curve plus add the entropy change associated with each of the transition, then the total entropy can be computed. But the only thing problem is, if you want to find out the value of Cp at very low temperatures, it is very difficult to calculate. So what do? You do an approximation of Debye extrapolation, which is known as Debye law, where the Cp is equal to A T to the power 3, where T is the absolute temperature we are talking about. And according to the Nernst heat theorem, at very low temperatures, if you want to calculate the entropy change accompanying any process, physical or chemical process or transformation occurring as the temperature is approaching zero is also approaching zero, provided the solid which you are having is perfectly crystalline. So what does the third law state? Third law is the manifestation is the Nernst heat theorem, which says that entropy of a system for any transformation is going to approach zero as the temperature is approaching zero, provided the substance is perfectly crystalline. Okay, that's the third law. Understood? So we are given the flavor of what the third law is, and third law is valid only when we are understanding the Nernst heat theorem, which is saying that entropy at low temperatures is going to approach zero, and that's a consequence of the Nernst heat theorem. And for calculating the total entropy change, what we need to calculate is when T is approaching zero, then the Cp is not just Cp what you have taken, but it has a new value which is coming from the Debye's law, and Debye law says Cp at very low temperatures should be taken as A into T to the power 3. A is some constant which is specified for different substances. Okay, so this is what we are having for the third law, and I hope I have made you understand as to what is going to happen for the entropy. Third law states that temperature equal to approaching zero, entropy is zero. That's the third law. But the only thing is you have to remember that provided the substance which you are taking into consideration or the process which you are talking about involves a substance which are perfectly crystalline. Only then you can approach the entropy equal to zero condition. Okay. So here is one example which I want you to look into. Calculate the entropy change when argon at 25 degrees centigrade and 1 bar in a container of volume 0.5 dm cube is allowed to expand to 1 dm cube and is simultaneously heated to 100 degrees centigrade. Have you taken down? Right? All of you?
Yes, ma'am.
Okay, now tell me, how will you compute the entropy? See, since entropy is a state function, we can choose a convenient path from the initial to the final state. So first path which we let us consider, when you are talking about entropy change associated with argon at 25 degrees centigrade at 1 atmosphere in a container of 5 say dm cube is expanded. So first let us take up only the expansion part. Let us say the expansion is carried out at constant temperature. So the first step I can compute is the reversible isothermal expansion, followed by a reversible heating at constant volume, right? I can do that. I have to go to the final temperature T 100 degrees centigrade, right? So first step, I can take that total change in entropy, since it is going to be only the initial and final values which we are interested. We are not interested in how the path is executed because entropy is a state function. So first I chalk out a path where entropy is changing, computing the entropy change for a reversible isothermal expansion. Okay, reversible isothermal expansion where the gas is at 25 degrees centigrade, 1 bar is contained in volume is 0.5 dm cube is changed to 1 dm cube. And the second part, I leave the volume constant at 1 dm cube and compute the change in temperature. I can do that. So what are the entropy changes? How we are going to calculate? Are you doing it?
Yes, ma'am.
Okay, so isothermal reversible expansion will give you a delta S value equal to NR ln V2 by V1 or V final by V initial. And what is going to happen for the second step? Volume is held constant. So instead of Cp, sorry, I have written in Cp terms, but you can write down Cv terms. Volume is held constant. So what you can find out, you can find out Cv dt integrated from T temperature of 25 to temperature of 100 degrees centigrade, right?
Yes, ma'am.
Now tell me, are you computing? Can you find out what the value is going to be?
Yes, ma'am.
Please do. And take this as an assignment. The expression will remain the same, but here you are doing a carrying out a cooling initial the gas, the same expression question we have is compressed to from 1 dm cube to 0.05 dm cube and cool to minus 25 degrees centigrade. This take it this as an assignment. Argon is a monoatomic gas. Okay.
Ma'am, it's coming 4R Ln2.
Compute it. The answer is given here, you see. Four R means it's going to be R is going to be quite high then.
Yes, ma'am, that's what I was thinking, but
Where are you going wrong? Have you put the substituted the value of N? What is the N which you have calculated?
oh yes, ma'am, I think I went wrong in the N values. Just a second.
Because here the N has to be substituted. This N has to be substituted, and that since I'm talking about argon being should be behaving as ideal gas. So ideal gas behavior, if you are considering, then you have to use the PV equal to nRT to substitute the N value. Okay, you do it in the time because we are going to be running out of time then. Anybody who's doing other than you?
Yes, ma'am, I'm doing.
What about the boys? None of the boys are doing? Please take up another question, another numerical. Calculate the entropy change when the same, whichever argon gas we are talking about, is compressed to 0.05 dm cube from 1 dm cube and cooled to minus 25 from 100 degrees. Yes, I want to hear from the boys. Please tell me what are you doing? Are you there in front of the computer, or you put on the computer and roaming around?
Yes, ma'am, I got that 0.173 joule per Kelvin.
Okay. And answer to this one is minus 0.44 joules per Kelvin for the assignment I've given you. Please check it and we'll talk about it later. One is done in the class. Just because you requested that I take up a numerical in the class, I've taken up, and I hope because you take time in computing and the lecture is held because of that. So in the class it is okay, but when you are having a lecture online, it becomes very boring. But I want to hear from the boys. Ankit? What are the names? I've forgotten the names also. No roll call. Ankit? Aniket, sorry.
Yes, ma'am. I'm here.
Ashish? Bhupendra? None of them are there in front. Vicky? Dharmendra,
Yes, ma'am.
you're there.
Yes, ma'am.
Fakhruddin,
Yes, ma'am, I'm here.
Gokul. Gokul
Yes,
is
ma'am.
not.
I'm here. I'm here.
Yeah,
I'm here.
yeah. Ishan. Ishan. Ishan is in Dubai, right? Shalik. Lekha.
Yes, ma'am. Likha.
Yeah, and Shalik.
Yes, ma'am, I got the answer of first one.
Okay. So we are done with the numerical. I have given you another numerical where you are supposed to report the answer in the next class or whether you have got it. See here you are going to get a minus. Minus because you are taking out a compression and cooling is occurring. So you have a minus. So the system is this and surrounding will be opposite to this if you are carrying out a reversible process. Okay. Now I want to come into the irreversible conditions. If I have a reversible process or a irreversible process for an ideal gas, what happens? When I have a change in state of an ideal gas going from T1 V1 to T2 V2 for the same number of moles of the gas, then I say that I can compute the entropy change by this expression, right? By this expression, where delta S is related to Cv ln T2 by T1 plus R ln V2 by V1. For an irreversible process, also if I want to calculate the entropy change, for the same process being carried out irreversibly from T1 V1 to T2 V2 for the same number of moles, the value I compute for the irreversible process is also the same. Okay? The value I calculate for the process being conducted irreversibly is also going to remain the same. That is because entropy is a state function and it's path independent whether you carry out reversibly or irreversibly. For the system, if I have to compute the delta S value, the entropy change value carried out reversibly will be the same way I calculate for the same state of change of state for carried out irreversibly. The expressions remain the same because we do not have any separate expression for irreversible process. And moreover, entropy change is path independent. So it doesn't matter where you are, how you are calculating the entropy change. But if the process is irreversible, then what happens for an isolated system? What you are going to have different is when you are having a change of state, say from state 1 to state 2, it is path independent. The total change in entropy should be the change in entropy of the final minus the entropy of the initial. It is going to be independent of the path you are choosing. But what happens to the surrounding if you are having an irreversible process in an isolated system? For an isolated system, the surrounding may not be the same as the system entropy of the system. Usually when you are having a reversible condition, whenever you are having a reversible condition, you can say that the entropy change of the system is going to be equal to the entropy change of the surrounding with a negative sign. They are equal and opposite. Okay, they are going to be equal and opposite so that the total entropy change of the universe becomes equal to 0 for a reversible process. Okay, that we had taken up in the previous class also. The entropy of the universe for a reversible change for isolated system is the summation of the entropy change of the system plus surrounding, where the system is equal and opposite to that of the surrounding. So the total entropy change becomes 0 for a reversible process in an isolated system. But what happens to an irreversible process? For an irreversible process, the entropy of the universe is going to be greater than equal to 0. That means the entropy of the surrounding will be greater than whatever entropy change you have for the system. This is said, it is important that we evaluate also. We are going to take one example where we are going to, not now because I have a sequence of things lined up, but I want you to remember that whenever you are talking about reversible and irreversible process, the system entropy change is going to remain the same. The process how you are going to calculate. But the same cannot be told about the surrounding. Surrounding for an irreversible process, for an isolated system, for the irreversible process carried out irreversibly for the same change in state, the surrounding will not be equal and opposite to the change in entropy of the system. It is going to be more than entropy change of the system, because the entropy change of the universe is going to be increasing. It's a negative positive value. So if you have something equal and opposite, then it is obviously supposed to be 0. But here what you have for an entropy change in the surrounding will be greater than that of the entropy change of the system. Okay, we'll take up examples later on. So for an isolated system, we can very clearly write down that the isolated system, how do you identify? We can identify the isolated system where for a reversible process, the entropy change of the universe is going to be 0. Entropy change is going to be of the universe is going to be greater than 0 if the process is spontaneous. And in all spontaneous processes, entropy will keep increasing. But entropy of a particular system may decrease, but the total entropy change of the system, of the universe, will be always increasing. This is the definition of the second law. The entropy of the universe of an isolated system will be always increasing. This is the condition which we have for the second law. Okay. Now, let us see, I have not discussed this actually. I want to discuss this part of the lecture. What is, when we say that entropy is increasing, continuously increasing, we are going to take up how it is going to do, how it is happening. But before that, I have not discussed the main part of the entropy discussion is the Cauchy's inequality. So Cauchy's inequality is given by delta S minus dq by t greater than equal to 0. And we know I'm saying here, but we actually do not know as far as the class is concerned. We have not discussed the Cauchy's inequality, though I have mentioned this in the when we were talking about the reversible engine being more efficient than an irreversible engine. That time we have talked about it. I don't know whether you remember that. I have said that this dq reversible, this dq by t actually contains two parts. It contains the dq reversible by t plus the dq irreversible by t. And if I sum dq reversible by t and the plus dq irreversible by t, that should be less than equal to 0. But so that from that I can say that entropy change which I associate is dq reversible by T. If I replace that dq reversible by T in that expression, then that will be all maximum value it can have is going to be 0. So 0 minus something will be always equal, greater than equal to 0, and it becomes equal to 0 when dq ds is equal to dq by T. That means that time we can say that dq irreversible part is not existing. I'm not able to make you understand until we write it down. It is difficult for you to understand. But as of now, we take one representation of Cauchy's inequality as ds minus dq by T greater than equal to 0, where ds is defined as the dq reversible by T. If you remember this, when I talk about the Cauchy's inequality, it becomes more clear. I want you to just remember one thing. Whenever I write dq by T and do not represent dq reversible, that means this dq is actually a composite of dq reversible by T and the dq irreversible by T. This will not be specifically written in any book, but you need to understand. When I write dq by T, that means it is having a combination of dq reversible by T and dq irreversible by T. Okay. So if I want to substitute here, what do I get? If I substitute dq reversible by T plus dq irreversible by T, what do I get?
We might get dq irreversible by T is greater than equal to 0.
But that is not what we mean. What we mean is dq irreversible by T will be less than 0.
Yeah, sorry, we have a minus sign also, so the inequality will change. So if we replace ds by dq reversible by T and we replace dq by T as a combination of both reversible and irreversible, so we might get dq irreversible by T is less than 0.
Less than 0, right? Are you everybody understood what I'm trying to say? You replace this, if you replace this dq by T in terms of dq irreversible by T plus dq reversible by T, and dq reversible by T is delta S, that will get cancelled. What is left is minus dq irreversible by T. So minus dq irreversible by T is greater than 0. So what you get, dq reversible by T, irreversible by T is less than 0. Yes, that is the Cauchy's inequality, that dq by T is less than equal to 0. Okay, so what we have discussed just now, that the surrounding entropy change of the surrounding for an irreversible process will be always increasing. For an isolated system, the surrounding is not affected, dq the change in the surrounding is not affected, so dq reversible for a reversible process or irreversible process can be taken as to be 0. dq is, for an isolated system, dq is equal to 0. Okay, for both reversible and irreversible change. For an isolated process, you do not have any heat exchange, right? For isolated, please understand what I'm trying to say. These are all written in the slide, and I reading through it doesn't make any sense. dq is equal to 0 for any process which is isolated, right? Which for any process, dq, the heat exchange between the system and surrounded for an isolated system is supposed to be 0. How do you compute the entropy? The entropy is always equal to greater than 0. So for any process occurring in an isolated system, entropy is always increasing based on this. And the entropy of the system will continue to increase as long as there are changes taking place. That's what I had just now said a few minutes back. And when no changes are taking place, that means the system has reached its equilibrium, and then the entropy has reached its maximum. So thus the condition for equilibrium in an isolated system is the condition where you have entropy as the maximum. Okay, and this is one criteria which I want you to remember, which we are going to discuss when we are going to say which is the condition or how long a process can continue to occur. A process in an isolated system will continue to occur till it reaches the equilibrium at which the entropy reaches its maximum value.